Okay, sir. Good evening to all. I'm going to present my pre-submission seminar on this is titled Development of Novel Dielectric Materials for Energy Harvesting Applications under the supervision of Professor P.M. Saru. These are the outlines of my thesis, introduction, which is followed by the synthesis procedure and characterization techniques. In third chapter, we have done the optimization of my of calcium copper titanate electroceramics at different temperature. Then detailed discussion have been done in chapter 4. In chapter 5, we have done rare earth doped CCTU electroceramic, and which is also discussed in chapter 6, the dielectric and electricity of post-transition metal and modified electroceramics, and conclusion, challenges, and future aspects at the last. Introduction. In first chapter, I have introduced some features of dielectric materials. A dielectric is an actually insulator that can be polarized when an electric field. And dielectric typically means material with a high polarizability because of the global environment concerns on the toxicity of lead-based materials such as lead zirconate, lead titanate. Scientists have impelled for the investigation of lead-free alternatives of high dielectric constant materials. Solid oxides such as SU3 and 402 double peroxide structure are suitable candidates for various technological applications because of their favorable crystal structures. CCTU, which is a member of SU3 and 412, has a cubic crystal structure with IM3 inverse bar space 2 has been drawn much attention because it's a lead-free composition and excellent dielectric and electrical properties in wide range of temperature and frequency. This is the objective of my thesis, finding the optimum synthesis condition for CCTU electroceramics to study the structural, dielectric, and electrical properties of the CCTU electroceramics, to explore the rare earth doped CCTU at calcium site, and to explore the post-transition metal ion substitution gallium at TI site. In chapter 2, we have discussed the material preparation, processing, and characterization methods. Among these methods, we have adopted solid state reaction method to prepare our sample. In solid state reaction method, after selection raw material and stoichiometric calculation, weighing were done, and 1 hour mixing without any medium, and 3 hour mixed with acetone as a medium, and then ground powder were calcined. Again, calcined powder were ground for 4 hours with acetone as a medium and dried 200 degrees Celsius for 4 hours. 4% of PVE was added to the ground powder for pellets for formation as a binder. Then circular shaped pellets were with diameter 12 mm and thickness 2 mm were prepared using hydraulic machine and then sintered. These green bodies were sintered. After sintering, conducting silver paste were coated on both the surface of pellets to make parallel capacitor. And these are the characterizations. For structural, we have performed XRD, Raman, and XPS for structural characterization, FSM, HRDM for surface morphology, and dielectric frequency and temperature dependent dielectric study, electrical modulus study, complex impedance study, and conductive study have been done with LCR meter. In chapter 3, we have structural and dielectric analysis of CCTU electroceramics at different sintering conditions. In this chapter, we have done the optimization of our sample CCTU electroceramics at different sintering conditions. These are the different sintering conditions. I have made 8 samples at different sintering conditions, in which XRD and residual refinement analysis have been done in this slide. Figure in all the samples, so all the samples so very good in high intensity peaks, and all peaks are matched with the standard database 0107521888, and in figure 3.1a, CCTU 101 and CCTU 02, there is no shifting in peaks take place while in CCTU3 and 4, shifting in peaks take place towards low breaks angle means expansion in lattice parameter takes place, which is also re-verified by the ritual refinement. And from CCTU05 to CCTU08, peaks are shifting towards low breaks angle, which means lattice volume also expanded, which is also verified with the help of ritual refinement. And this is the surface morphology of the optimized all 8 samples, in which clear grain boundaries, dense and compact grains are observed. These are the parameters obtained by the ritual refinement and microstructural analysis. Frequency dependent, now we have done frequency dependent dielectric characteristics at room temperature from CCT01, CCT02, CCT03 and 4. From all these dielectric constant and transient velocity, it is observed that all have, except CCT01, all materials, uh, all samples have a relaxation peaks, which means these samples are not very good and not very applicable in application based material. From CCTU 5 to CCTU 8, very good trend is following with the increasing the tangent dielectric constant and decreasing the tangent loss. And at CCT08, we have obtained maximum dielectric constant and minimum tangent loss. So from these, which is given in the table from CCT01 to CCT08, it's dielectric constant and tangent loss. From in conclusion, we can say, from based on these observations, we can say that CCT08 is the optimized electroceramic, which is calcined at 950 degrees Celsius for 6 hours and sintered at 1050 degrees Celsius for 4 hours. Now, in this chapter, we have done the full detailed discussion of optimized sample frequency and temperature dependent dielectric and electrical properties of CCTU electroceramics at optimized sintering temperature. Structural and for structural and microstructural analysis, we have done a ritual refinement of optimized sample. And for convenience, we have changed CCT08 with the name CCTU00. So ritual refinement is done of optimized sample, and by figure 4.1 B, show the FSM image of CCT00 electroceramics, from which it is confirmed that big grains are formed, and between the big grains, small grains also observed, which means by model distribution of grains is observed, and average uh, grain size is obtained with the help of histogram, which is 127.35 micrometer. And this is the HR-TAME and Raman study. In figure 4.2, so the TAME, B, HR-TAME and C SED pattern, and 1, 2, 3 are the enlarged view of HR-TAME image for CCTU00 electroceramics. With the help of TAME, we can calculate the particle size, which is ranges from 18.402 nanometer to 50.948 nanometer. And from enlarged view of HRTM, we have seen that we have selected 3 regions in which fringes are clearly observed. Between interplanar spacing, we have obtained the value of interplanar spacing 0.301 nanometer, which is corresponding to 211, and 0.538 nanometer, which is corresponding to 110 Miller indices, and 0.184 nanometer, which is corresponding to 400 Miller indices. And in a CD pattern, we are seeing that we have seen that three circulars are formed, which is corresponding to 2 to 2, 3 to 1, and 1 to 5, which means HR-TAME analysis consistent with the XRD pattern of the CCTU electroceramics. In figure 4.3, Raman spectrum for the CCTU00 electroceramics is observed. There are 3 Raman detected mode are seen: AZ1, AZ2, and FZ3. Ag1 is obtained at 445 centimeter inverse, 570 at Ag2, and 510 centimeter inverse Fg3. Ag1 symmetry is because of the TiO6 rotational lattice vibration, while Ag2 and Fg3 symmetry is because of the OTI or type antisymmetric stretching vibrations. Now XPS study. In XPS study, we have done full range XPS survey scan spectrum and the elemental survey scan spectrum of calcium, copper, titanium, and oxygen. From calcium, narrow range spectrum of calcium, it is clear that two peaks are observed at 346.40 electron volt and 349.90 electron volt, which are corresponding to Ca2p 3 by 2 and Ca2p 1 by 2. And for copper, there are three peaks are observed, Ca2p 3 by 2, and two peaks are the satellite peaks. After deconvolution of Cu2p 3 by 2, Cu3 positive, Cu2 positive, and Cu positive, three states are oxidation states are observed of copper at 935.10, 934.00, and 932.70 electron volt. When we done the narrow scan of titanium, then we have find two peaks at Ti 2p 3 by 2, Ti 2p 1 by 2. After deconvolution of Ti 2p 3 by 2 peak, there are two oxidation states of titanium is observed, Ti 4 positive and Ti 3 positive. At the binding energy 458.60 electron volt and 458.00 electron volt. In oxygen, there are two peaks also observed at 529.80 electron volt and 531.70 electron volt. One peak is corresponding to which are corresponding to lattice oxygen at the lattice, and as another at the surface of the material. Now, this is the dielectric analysis in wide range of temperature and frequency. 4.5 in 4.5 A frequency dependent dielectric constant is have been studied. From a figure, it is observed that with increase of temperature, dielectric constant is also increased, which means thermally activated charge carriers take place. And with increase of frequency, dielectric constant at low frequency from 100 hertz to 10 to the power 5 hertz, almost constant at low temperature, approximately 100 degrees Celsius. Then for all the temperature, a change is observed from 10 to the power 5 hertz to 10 to the power 6 hertz, which means conducting charge, conducting grains will take place at this region. And for more discussion, we can for more explanation, we can explain it with the help of IBLC model, internal barrier layer capacitance model, in which dielectric constant can be calculated with the help of formula given below. Epsilon effective equals to epsilon gb tz upon tzb. Epsilon effective is the overall dielectric constant of the material. Epsilon gb is the grain boundary dielectric constant. Tz is the average thickness of the average grain size, and tzb is the grain boundary thickness. So, according to IWLC model, the tangent loss in CCTU electroceramics is also can be calculated with the help of this formula. Tan delta equals to 1 upon omega RGBC plus omega RGC. At tan delta is from this formula, we can explain very well that at low frequency low frequency RGB is dominated. Grain boundary resistance is dominated. Then tan delta become 1 upon omega RGBC, which means omega RGC will be negligible. Tan delta become 1 upon omega RGBC. Then at low frequency, tan delta is minimum. Well, with increase of frequency, tan delta equals to omega RGBC, as in high frequency grains are dominated. So 1 upon omega RGBC term will be diminished, and tan delta will be omega RGBC. So at high frequency, tan delta become maximum, which is confirmed by this formula. And I will see model among different models. I will see model the best model to explain the dielectric constant and tangent loss of the CCTU electroceramics. Figure 4.6 represent the temperature dependent dielectric constant and tangent loss of CCTU electroceramics. From this, we can say that with the increase of the frequency, stability is increases from at maximum stability is observed at the 1 millihertz, while the tangent loss is very disturbed in nature in 1 megahertz. So we can say that 1 kilohertz, 10 kilohertz, and 100 kilohertz are the best stable frequency range, and there is no phase transition is observed in this by the temperature dependent dielectric constant. Temperature coefficient and conductivity study. Temperature coefficient from room temperature at which is temperature coefficient is calculated from room temperature to 200 degrees Celsius, which is less than 15% from room temperature to 140 degrees Celsius. Now, in conductivity analysis, figure 4.8 represent the frequency dependent AC conductivity, which is follow the Johnson power law, which is given as omega sigma AC omega equals to sigma DC omega plus k omega n. So as if omega equals to 0, then sigma AC will be sigma DC. Means if at lower frequency range, with increase of temperature, the conductivity is also increases, and flatness is increases. Flatness means which is parallel to the x-axis, means independent of the omega and applied angular frequency, which means long range motion of electrons take place at the low frequency region, and with at high frequency region there is a linear region which comes according to short range motion of charge carriers, and nearly constant loss take place. And in figure 4.8b, linear fitting of DC conductivity of CCT00 electroceramics is obtained, which is activation energy is less than 0.41, which confirm that the conduction mechanism in CCT0 optimized sample is because of the hopping of electron or oxygen vacancies. Complex impedance study. From complex impedance study, we can obtain the grain and grain boundary contribution in dielectric constant from figure 4.9a. Real dielectric real component of impedance is observed at low frequency. Impedance is dispersive nature, which means at low frequency space charge polarization is absence. With the increase of frequency, all plots are merged at one, which means space charge polarization is present as the absent as the high frequency, which is because of the drop of barrier height and electrode effect. And CC and 4.9b represent the imaginary component of impedance of CCT electroceramics, in which at a low frequency there is a dispersive nature of Z double prime is observed, which means space charge polarization is present, and high frequency space charge polarization is absent. With increase of frequency, relaxation is shifting towards a high frequency, which means relaxation is because is temperature dependent. At low temperatures, relaxation is because of the immobile species or electrons, and at high temperature, relaxation occurs because of the defects and vacancies. A plot figure 4.10 show the Nyquist plot. A plot between Z prime and Z double prime is known as the Nyquist plot. And with the help of Nyquist plot, we can find out the grain boundary resistance and grain resistance, grain resistance. So to obtain the two semicircular, this is fitted by two semicircular arc RG and RGB. RG are the two semicircular arcs which are representing RC circuit. One semicircular arc means one RC circuit. Two are connected in series combination with parallel RC circuits. At diameter of this semicircular arc represent the RGB, while the non-zero intercept at higher frequency represent the RG. And and electric modulus study have been done with the help of these formulas. M dash and double dash can be calculated. At figure 4.11 represents the real modulus of dielectric of real modulus of electricity 00 electroceramics. From figure, it is clear that at low frequency side, real modulus is approximately zero, which means negligibility of the electrode polarization at lower frequency. And with increase of frequency, a monotonic dispersion take place, which is due to the conduction phenomena and short range mobility of charge carrier. This confirms that the insufficiency of restoring force for the flow of the charge carriers under the effect of stereo electric field. Now, figure 4.11b represents the imaginary component of modulus of CCT00 electroceramics, in which omega maximum tau equals to 0 separate a short range to long range motion. Omega maximum and tau is a relaxation piece. Omega maximum is the frequency at the relaxation peak. If omega maximum tau is greater than 1, which means long range motion of which means short range motion of charge carrier take place, and if omega maximum tau is less than 1, which means long range motion of charge carrier take place. And the dependence of peak intensities on the temperature verify the dependence of the capacitance of grains and grain bonding on the temperature. In conclusion words, we can say that bimodal distribution of grains is observed with the average grain size 127.35 micrometer. HRTM results are consistent with the XRD patterns. XPS analysis confirms the oxidation stress of electron present the CCT00 electroceramics. The temperature dependent dielectric constant confirm the absence of any phase transition. Thermal coefficient is less than 15% from room temperature to 1 to 40 degrees Celsius, which means CCT00 is very useful for practical applications. Now in chapter 5, structural and microstructural analysis of rare earth dot CCTO electroceramics, we have chosen two rare earth holmium and iridium, which is nomenclature is given in the table 5.1. Study of holmium dot CCTO electroceramics SRD and reticle refinement from figure 5.1. Figure 5.21 show the XRD patterns of the HCCTO ceramics, in which all the peaks are well matched with the standard JCPDS 0. Given inside of the table. With increase of concentration, the peaks are shifting towards a high Bragg angle, which means shrinkage in lattice balloon take place, which is re-verified by the ritual refinement. And except impurity except SCCTO03, no impurity phase is obtained, and SCCTO03 impurity phase is obtained of TiO2. And but there is no impurity phase of holmium is obtained, which means holmium is totally substituted towards the at the CA site. This is the surface morphology of the SCCTO ceramics. From SCCTO02 is the sample in which maximum grain growth is observed. And the average grain size is 5.84 micrometer. From figure 5.4, EDX spectra of SCCTO electroceramics is observed, which can, with the help of EDX, we can find out the elements present in the sample. Raman study, there are 3 Raman detected modes are observed as in previous and in chapter 4 we have explained AG1, AG2 and AG3 symmetry. In because of the substitution of holmium, a Raman band is obtained 569 to 572 centimeter inverse corresponding to AG2, and for 506 to 509 centimeter inverse corresponding to FG3. And parameters obtained by structural and microstructural analysis are given in the table. Frequency dependent dielectric analysis. In frequency dependent, with the help of IBLC model, we can explain the dielectric constant and tangent loss as I have discussed in chapter 4. So epsilon prime maximum dielectric constant is observed in SCCTO 02. Which is very high dielectric constant, and it is approximately 26% greater than that of dielectric constant obtained at the room temperature at the HCCTO 00, and minimum tangent loss is observed at HCCTO 02. Tan delta equals 0.08, which is very less and useful for practical applications. Temperature dependent, from temperature dependent, it is clear that there is no phase transition is observed. Conductivity analysis, from conductivity analysis we can find out that activation energy for all SCCT 0 to SCCTO 03, activation energy is less than 0 point less than 1, which means conduction in SCCTO 0 SCCTO ceramics is occurred with by either a hopping of electrons or oxygen vacancies. Complex impedance study. In this slide, we will explain whole theory of complex impedance study, in which see there are actually contribution of grain and grain boundary can be explained with the help of Nyquist plot, in which two RC circuit are shown. One is corresponding to grain and other is corresponding to grain boundary. So it must be two semicircles must be obtained. But because of the high frequency limit at the room temperature in LCR meter, we obtain a one semicircular arc, and which is corresponding to at high frequency grains are dominated, at low frequency grain boundary is dominated. So we can obtain the value of RGB, means grain boundary resistance, with the help of diameter of this Nyquist plot and the non-zero intercept at the high frequency. We can obtain the value of RG, and the activation energy obtained by the and C where C equals to R 1 by n q 1 to the whole power 1 upon n. Q is the constant phase element, so we can obtain the value of capacitance of material. So their activation energy obtained by the linear fitting of grain resistance and grain boundary resistance is given in the table, which is from 0.3, which is from 0.3 to 0.5 for grain, and 0.10 to 0.47 for grain boundary. These are the results obtained after the best fitting of Nyquist plot. Modulus study, as we have discussed in earlier slide, that non-debye type nature is obtained. We can obtain by the imaginary impedance, imaginary component of modulus, and from real component of modulus, we can explain that the electrode polarization is absent as the at the lower frequency side. This is now we will go towards the study of erbium doped CCTO electroceramics, XRD, and retrieval refinement. All the peaks are well matched with the standard JCPDS, and there is no impurity phase is obtained in erbium doped CCTO ceramics. And with increase of with increase of concentration of erbium, the peaks are shifting towards the high Bragg's angle, which means linkage in lattice volume take place, which is re-verified by the retrieval refinement, and the value obtained by the retrieval refinement for ECCTO ceramics are given in the table 5.4. Surface morphology. From surface morphology, it is clear that with increase of erbium concentrations, grain growth is decreasing, which is a common phenomenon in rare earth doped element. At the maximum grain growth is observed ECCTO 01. So so according to IBLC model, maximum dielectric constant must be of ECCTO 01, which I will see in next slide. Raman study, there are three Raman detected mode is observed as in previous slide, which is in which 443 centimeter inverse, which is corresponding to AZ1, and AZ2, FZ3, 569 to 572 centimeter inverse, and 502 to 510 centimeter inverse. And parameters obtained from the surface morphology is given in the table 5.5. Frequency dependent dielectric constant and tangent loss. As we have discussed in IBLC model, that if silent GB and if silent effective equals to if silent GB TZ upon TZB. So if grains average grain size is maximum, then dielectric constant must be maximum. So it is very clear here that grain size is maximum for erbium dot for ECCTO 01, which is and maximum dielectric constant is obtained for ECCTO 01, and minimum dielectric loss is obtained for tan delta. So it follow the IVLC model. From temperature dependent dielectric constant tenure loss, it is clear that no phase transition is occurred in ECCTO ceramics. This is the temperature coefficient of ECCTO electroceramics at room temperature. If the temperature coefficient at room temperature is less than 15%, then that material is very useful for energy storage applications. Temperature coefficient can be calculated with the help of this formula. T is where T is the temperature at which we can find out the temperature coefficient. Epsilon dash is the dielectric constant of the material. So from this figure, it is clear that from room temperature to 130 degrees Celsius, temperature coefficient is less than 15%, which means this material is very useful for the energy storage applications. Conductivity is a study. From conductivity study, it is very clear that that with increase of erbium concentration, grain size is decreasing, which means the conductivity is increasing, and which is also clear by the figure. Activation energy is less than one, which means hopping electrons or hopping of electrons or oxygen vacancies take place in the conduction mechanism. Complex impedance study, which is also explained in the previous in the last slide. Holmium dot is CCTO ceramic. That this is formed with two RG circuit connected in a series. One is for grain bondier, second is grain, and activation energy is obtained with the help of grain resistance, and grain is given in the table 5.6, which is between 0.10 to 0.43, and EZB is 0.23 to 0.40. The parameters obtained after the base fit of Nyquist plot is given in the table 5.7. Modulus study, with the help of modulus study, we can find out the nature of material, which is divide type or non-divide type. So relaxation peaks are asymmetric, so we can say that it is non-divide type material. In concluding words, we can say that magnitude of the temperature coefficient is less than 15% from room temperature to 130 degrees Celsius, which confirm that CCTO ceramic is useful for energy storage application. Comparing the dielectric and electrical properties of holmium and iridium modified CCTO ceramics confirm that holmium dot sample has better alternative to dielectric capacitor at suitable temperature. In last chapter, structural and microstructural analysis of gallium dot CCTO electroceramics has been studies, and nomenclature is given in the table 6.1. XRD and ritual refinement. From XRD, it is clear that all peaks are well matched with the standard database, while all concentration except CCTO 02 impure phase is obtained, while TiO2 is impurity phase in CCT 002, and which is re-verified by the ritual refinement also. The surface morphology, it is clear that surface morphology, it is clear that maximum average grain size is obtained for CCTU02, CCT02, which is given in the table 6.2. HRTM and Raman study figure 6.4 so the HRTM of CCT00 and CCT02, in which from TAM we can find out the average particle size, which is given in the figure, and from CCT0 and CCT0 HRTM we can find out the interplanar spacing between the fringes between the interplanes, and which is given in the insets of the figure. We have chosen three different positions in HRTM, which are well matched with the well matched and consistent with the XRT pattern. And CCT0 and CCT02 are the SAD pattern, in which four circles are obtained four circles are obtained in CCT0 and CCT02 also, which are consistent with the XRD pattern. In Raman study, we again find the three Raman detected mode at 444 centimeter inverse AZ1 and 469 to Raman band is obtained 469 to 572 AZ2 and 5 FZ3 is 508 to 510 centimeter inverse. XPS study. From XPS study, we can find out the oxidation state of calcium, copper, titanium, and titanium, oxygen, and gallium. Figure 6.6 so the full range XPS survey scan spectrum of CCT02 electroceramics. Well, in calcium, there is two peaks are observed at 345.94 and 349.46. So it is we can say that calcium is present in Ca2 positive state, and CCT02 for copper we can say that there are copper is present in three states, and titanium are present in two states, Ti4 positive and Ti3 positive, while oxygen present in OL and OS, which is OL means lattice, oxygen present at the lattice and oxygen present at surface. In gallium, there are two peaks are observed at 1144.89 and 1117.91, which are corresponding to gallium 2p1 by 2 and gallium 2p3 by 2, which means gallium is present in Ga3 in Ga3 positive states. Frequency dependent dielectric constant, maximum dielectric constant is obtained for CCT02 as from the IBLC model. Maximum average grain size means maximum dielectric constant, and minimum value of tangent loss is observed in CCT02. Temperature dependent dielectric constant so that there is no phase transition is observed also in CCT0. CCT is CCT0, CCTGO electroceramics. Conductivity study. From conductivity study, we can say there are three regions are present. One is the low frequency, medium frequency, and high frequency. In high frequency, we have explained the low frequency and medium frequency. In here, third reason is also appear in high frequency, which is because of the absence of charge polarization. As activation energy is less than 0.1, which means conductivity is because of the hopping of electron or oxygen vacancies. Complex impedance study. From complex study, we can again find out the contribution of grain and grain boundary resistance, and grain boundary resistance, which is given in the next table, and activation energy obtained by the grain resistance and grain boundary resistance in given the table 6.3. These are the parameters obtained after the base fit of the Nyquist plot. In conclusion words, we can say the maximum dielectric constant is obtained for x equals to 0.06, that is CCT002 with value with the highest value and tangent loss, minimum tangent loss. In chapter 7, now we can move towards the conclusion and challenge and future prospects. These are the conclusions. Dielectric constant for holmium doped sample is higher than that of erbium and gallium with the least tangent loss. Temperature coefficient is less than 15% from room temperature to 130 degrees Celsius for erbium doped CCTO, which confirm better application in energy storage. Grain and grain boundary contribution is analyzed by Nyquist class. The conduction mechanism responsible for conduction is the sample is oxygen vacancies or hopping electrons. Modulus analysis confirms the non-debate type behavior of CCTU electroceramics, while results obtained from dielectric and electrical measurement understanding and utilizing lead-free ceramics for electronics are expected to provide an additional feature for better device application. Acknowledgement, my heartfelt gratitude to my PhD supervisor, Professor P.M. Saroon, my sincere acknowledgement to DSC members, Professor P.K. Anthony, Chairperson Professor S.K. Sarma, Professor Rohit P. John, Department of Chemistry, present HOD and former HODs of the department, present director and former director of the institute, all the faculty members of the Department of Physics, all the staff members of the Department of Physics. I'm also very thankful to the IIT Dhanbad for providing a research fellowship and contingency grant. I acknowledge to CRF of IIT ISM to accomplish this work by providing various characters and techniques. I'm very thankful to friends, family, and lab members of the functional ceramics laboratory. These are the list of publications. list full length paper published in conference proceeding. This is the old title, and this is the proposed title.